Okay, so let's get started. And so first of all, I would like to thank everyone who attend this very first talk hosted by the AI Talks. So thank you everyone, and good morning, and perhaps good afternoon and good evening. So I would like to introduce our very first speaker, Chunyuan Li. So Chunyuan is currently a principal researcher in the deep learning team at Microsoft Research, and he obtained his PhD at Duke University, where he works on probabilistic deep learning. And he also has spent time with, he also has worked on some well-known institutes like Uber AI, Adobe Research. And he is currently working on large-scale pre-training in computer vision and vision-language multimodality. And his research has been published in many top-value conferences, including NeoRIPS, ICLR, ICML, and CPPR. I think those conferences, if you guys are working on the field, you should know what they are. So let's get started. And Chunyuan, you can go ahead and start whenever you are ready.
Yeah, thank you for the invitation, and thank you for the introduction. It's my great pleasure to do a presentation here. Especially, I just learned that this is the first part of this series. So very happy to be here. So today I'm going to share our recent work on vision and language approach to tackling the problem of computer vision in the world. And let me first share you about the research presentation agenda for today. So basically, there are two parts I want to share. And first one is about modeling, and the other one is about the benchmark. So my major goal today is trying to advocate our recent efforts on the common benchmark and challenge. But to do that, I have to go back to talk more about our work on modeling. Hopefully, those give you a strong motivation why benchmark, a common benchmark, is important. So the key word for the modeling part, I think, is just one word: reformulation. So internally, like in our team, we have a slogan which is saying, every visual recognition problem is a vision language problem. So I'll use two stories to tell you why and how we can reformulate these computer vision problems, especially those visual recognition problems, as a vision language problem. And for the two stories, one is UniCL, where we reformulate image classification as image text matching. And for GLIP, we reformulate object detection as a phrase grounding problem. And after that, we will see some advantage of this formulation, especially I'll use KLITE to illustrate the advantage of the reformulation. So first of all, let me try to give some background. So we all know that image classification and object detection are two important computer vision tasks. And with recent advances in deep learning, and this community have achieved great results on internet and COCO. However, when we think about the real-world applications, and there are many interesting real-world applications. For example, for the recognition and the action recognition, and especially now when we deal with COVID-19, it actually generates new applications. For example, the detection of mask wearing, or the detection of whether our package is delivered or not, right? So and it means that in the real world, we often have many new computer vision applications. And if we think about this, so when a well-trained model on internet and COCO, and it's very hard for those models to immediately generalize to those downstream applications in the world. So we see a gap here, right? So for those interesting applications in the world, and we see that there are three challenges for us to tackle. And the first one is open set recognition, or open vocabulary recognition. And I think this is a recent trend in computer vision. And second one is about domain adaptation, because we are talking about thousands of downstream AI applications. It often means that very likely we may have images whose visual content is in a different domain. And the last one is about efficient transfer or effortless transfer. I think this is an important requirement when we build vision foundation models. It means that when the model is developed, this model should be easily transferred to downstream in a zero shot or field shot learning transfer setting. So to tackle this problem, to tackle these challenges, we are considering a vision language approach, and especially like we human beings are surrounded by various types of different types of digital media, right, including image, video, and language. And the question we are asking is that, if we can build one foundation model so that we can use this foundation model and transfer it to many downstream AI applications. So, like solving any AI problems, I think the very first thing is to get familiar with our data. Perhaps this is the most important thing before we dive into modeling. Let's take a look at the spectrum of vision language data. So I will divide it into three categories. The first one is image data only, and this is mainly a setting that we're a setting where image self-supervised learning model is applied. I think the promise of this type of approach is that we can often get infinite number of images from the internet. So it means that the data scale is really large. So if we can design some efficient and effective self-supervised learning method, so in theory, we could really scale up, right? So I think a lot of people in the community is still working, is actively working on self-supervised learning to train a visual backbone. Some popular methods like contrast learning or mask image modeling. So we can also take a look at the second category of data. I'll call it as like clustering image language data. So for example, the image and the sentence that I'm showing here, right? So we already have the global correspondence between this image and the sentence. So when we look at the data scale, so there are some high quality public data in this category. For example, for image label data, we have internet 22K, and for image caption data, we have CC12 media. And those two represent the high quality and constrained language image data. And of course, like we also have some larger data sets, but the quality is a little bit worse than those high quality data. But at least it gives some promise that we can scale using constrained image language data. And the last one is the fine-grained language image data, where we have the correspondence between the phrases and words in the sentence and the regions in the images. So if you look at the data scale for this category, and it is quite small, especially when we compare with the other two categories of data, right? So overall, it means that there is a trade-off between the data scale and the semantic and the richness of the semantic. This is the overall data spectrum we have for the current public vision language data. Of course, in some companies, and we have the private data, which is like become important for them to achieve software performance in some applications. So in this talk, I'll first use two stories. One is UniCL for the coarse grade data, and the other one is GLIP for the fine grade data. And I'll use these two stories to tell you that how we do the reformulation. So the first one is unified contrastive learning. So this is applied to the course grade language image data. So let me first introduce a new image, text, and label space. And the text here can be any text simple description. It could be as simple as a category name, or it can be like a more descriptive caption. And the label here, I think we have our own definition. The label here is defined as the index of the unique language descriptions. Notice that this is just a discrete index. It has nothing to do with the semantics of the category name. And the third dimension is an image only, right? So now we can use this joint space to study some of the well-known algorithm or the learning paradigm to train visual backbone. And the first one is self-supervised learning with images only, because it only uses images and it has nothing to do with text and label. And now we have the standard supervised learning, where we learn from the textbook, right? So the goal is to map the input image to discrete labels, and where we don't use any text information at all. And now recently we also have the language image learning, where we are using the image and text contrastive learning, and we don't consider the underlying relations between the text or the image. And so we say that, like, if we use the label, image, and text triplets, we see that for each method, there is some missing data, right? For example, for supervised learning, we are missing the text information here. And for the contrastive learning, we are missing the label information here. And this actually motivates us to design our UniCL algorithm, where we try to leverage the full spectrum of data. And so I'll skip the details. And so by leveraging the triplet data, and we also define the unified contrastive learning training objective, this can recover to the supervised learning and recover to the standard contrastive learning and the supervised contrastive learning in theory. And by scaling up the training objective, and this leads to the methods of the Florence model, which is trained on a large amount of image text data and with larger models. And it shows many sort of performance last year. Then I'll tell you a second story, which is for the fine-grained image and language data, and we call it a grounded language image training of GLIP. And the story is similar to what I showed earlier for UniCL, and we are just doing it at the region and the phrase level. So let me first tell you what is the phrase grounding task in vision and language. So this is a relatively smaller research topic. So for phrase grounding, so we are given a sentence and an image, and the goal is to for some phrases in a sentence, the goal is to find its corresponding boxes in the image, right? For example, the woman here in the sentence is highlighted by a green box in the image. This is the definition of phrase grounding in vision language. And in ComputerVision, we have the well-known task called object detection. And one of the main contributions of the GLIP paper is to show that every object detection problem can be reformulated as the phrase grounding problem. So we can do it by simply concatenate all the category names for that object detection task as a sentence. You can imagine for Coco, there are 80 category names, or 80 concepts, right? If you concatenate all of these 80 concepts in one sentence and use it as a prompt, So in terms of format, it's actually in the same format with the phrase grounding problem. And by unifying these two type of research problem, it can actually give us the same interface so that we can leverage both type of data in the public domain, right? So you might want to say that okay, it seems that the phrase grounding data is so tiny compared with the object detected data, right? But the better thing, the good thing is that we can allow the self-training so that we can pseudo label on the image text data so that we can get a lot of fine-grained pseudo image and text pair, pseudo phrase grounding data. So by doing this, and now we can say that for UniCL is trying to unify image classification problem and image text retrieval or matching problem, and we are using the same objective. And for GLIP, we are unifying the object detection problem and the phrase grounding problem, and we are training it with the same objective. So these two stories show you that we can actually unify or reformulate the visual recognition problem to this vision language problem, and then we can train it with a larger amount of data. Okay, so you might be wondering, so what is the benefit at all, right? After the formulation. So we see one common thing after we reformulate the computer vision problem as a vision language problem. The unique thing is this language encoder, right? So in both UniCL, even KLITE, and our GLIP, we see that the language encoder is the unique thing that we have introduced for those models, right? So that's why we are wondering if we can push this direction and make the language play a much more important role for vision, especially for visual recognition problems. And so, inspired by this, and like we introduced one more piece of work on modeling, which is called KLITE. It's trying to leverage external knowledge using the language encoder so that we can get a much more efficient pre-training objective. And the other thing is that with this language encoder, and we are able to do open set recognition, and we can further pre-train a foundation model so that we can transfer to a large range of downstream tasks. And then if necessary, we introduce a problem that how we can do the benchmark in a relatively fair way. And then I will further talk more about these two pieces of work. So, and that is in master slide, I show like our recent ideas on how to push the direction of vision language for computer vision. And in the research community, we also see a trend that people are actively pushing this direction. So I think it all starts with this GLIP or the Google Align work, right? So on one side, and so inspired by GLIP inspired by GLIP and Align, and people say that maybe image text learning is the most practical way to train a visual backbone, and that's why in many big tech companies you have seen that they now have their own version of GLIP, right? And this is perhaps the most powerful approach currently to train a visual backbone that can transfer to many downstream visual tasks. And on the other hand, we think that the idea of open set recognition or task level transfer now is used not only for image classification problem, it also inspires people to work on other visual recognition problems. For example, object detection, segmentation, and video classification. I think like with these two directions, and it's possible that we can gradually move towards to the goal of computer vision in the world. So I also want to mention that now there is also a trend that we are moving from the in the research community, we are moving from this class level transfer to the task level transfer. So let me try to give you some definitions from my own perspective. So for the traditional class level transfer, so the key is that in a given single domain, right? So the key is the object classes that the instance for a given object class should never be observed during training, right? And we are trying to generalize to unseen object categories, but the visual domain remains relatively close. But for the task level transfer, so the key is that now we are trying to transfer to new tasks or new data sets. And the key is that as the training instances, the training image instances should have never been observed during training. And this is the key difference between these two paradigms. And so with this definition, and I want to put our recent work, KLITE and elevator, in comparison with this with the traditional approach. So, for example, in modeling, eternally it has been leveraged for the class level transfer, but it has never been used for the task level transfer. That's why we introduced KLITE to study the effectiveness of external knowledge. And in terms of benchmark, and there are several well-known benchmarks for class level very short transfer, but it's often done in a single domain, right? And now we are moving to the task level transfer. Whether or not it means that whether or not we can train a foundation model that transfers to many data sets or many tasks, and we also introduce elevator to achieve that. So now I'll gradually go to the details of KLITE, which is trying to learn a generic visual backbone with external knowledge. So let me start with a motivation example. So leveraging external knowledge is a common approach that we humans often use to make visual recognition decisions our data. Imagine the first time that we are in a Japanese restaurant and we are offered with a menu with some dish names only, and for example sashimi, right? So imagine this the first time, and it would be very difficult for us to understand what they are, and not to mention how we can recall their visual appearance, right? But after the waitress explained the concept using her own knowledge, and we may immediately have a better idea of the visual appearance of the dish, right? And therefore we can order the correct dish that we have imagined. So similarly in many domains, we often have some domain-specific knowledge, for example, textbook and a database. And the goal of this project is, can we actually design some systematic approach to mimic how humans learn or recognize novel concepts? So for humans, so instead of memorizing all the concepts, right, we humans actually leverage some structural knowledge so we can generalize effectively. So in terms of the concrete algorithm, it is quite simple. So for example, for the traditional language and image training algorithm, no matter it is like contrastive learning or generative learning, so we are only use image and language data. And in our algorithm, so we actually expand or augment the language modality with knowledge. And the way we do it is, given a sentence or given some text sentence, we extract the entities from the language, and we then use it as a query and retrieve the related knowledge from a database. And in this project, the knowledge base is simply defined as a dictionary or word net. And after we get the retrieval knowledge, which is represented as a text sequence, now we can also we concatenate the retrieval knowledge sequence with the original language sequence, so that we get a longer sentence, and that is used as a supervision signal for image learning. So at the baseline, the supervision signal is only from language. So now you already realize the difference, right? The main difference is that we are learning on this like image, language, and knowledge data data spectrum, while the baseline is learning with only image and language. So we apply this idea to two computation problems. One, the UniCL, where we train on a large corpus and transfer to many image classification problem. And we also apply it to GLIP, where we train on O365, which is a large object detection data set. And then we transfer to several downstream object detection tasks. Let's take a look at the results. So I think our baseline is UniCL, and UniCL is the academic version of Microsoft Florence. And UniCL is trained on large public academic data sets. So I think the main takeaway message is that UniCL, compared with UniCL, and external knowledge can significantly improve the sample efficiency in pre-training. For example, we can achieve better or comparable performance compared with the UniCL by using only a half number of image characters. And this is evaluated on zero-shot performance on internet 20 and zero-shot and linear plotting performance on 20 image classification data sets. And if you are interested in why external knowledge can improve the performance, and we provide the breakdown and analysis over here, and you see that the data set or the scenario that external knowledge improve them benefit the most is with fine-grained image classification problems. And because oftentimes for those downstream applications, and it contains real concept and real knowledge. So external knowledge can explain this real concept using some common concept or common word, so that the model can understand the concept better. So we also apply the ideas to object detection, and similarly we see some improvement on zero-shot object detection in downstream data sets. Now I'll introduce the last part, the benchmark. So we have said that in the community, we are actively creating new models, right, for open set recognition, including image classification and object detection. And we are trying to do it in a task level transfer fashion. But the problem is there is no common benchmark and toolkit, and so that people can measure the progress concretely. And this motivates us to build this elevator benchmark and toolkit. So as I mentioned before, so in with recent language augmented solution models such as GLIP, right, and we see these opportunities to creating new models that can do task level transfer. But if you look at the recent released models, and especially for the image classification, for the zero-shot image classification models, right? For example, maybe in Google they have like Align and Coca and LIT, and in Facebook we have Lava And maybe in some Chinese companies, we have data equals CLIP and daily, and so on. So if you look at the benchmark they are using, and typically we have a customized set of image classification data set, and they evaluate on like their shot, right? And but I think it is very hard to say that which model is performs better than the other, and because typically they often use like the data set that may performs better for their old model, right? That is one thing. And the other thing is how this model is adapted to the downstream data set. For example, when you do linear prodding, when you do fine tuning, or when you do few-shot learning, and those details is not transparent. And the goal of our project is that how about we build a benchmark and toolkit and make it open source so that people can measure it in a more transparent way. So this is the details and data statistics for this benchmark. So overall, we have 20 image classification data set and 35 object detection data set. And for each of them, we augment the language part with external knowledge, and so that the language part is enriched and which could be used as like some knowledge aware of content, knowledge aware of prompting approach, so that we can use it to improve their performance. So compare with the literature, and we see that ours is more like a set of data sets, and we augment with external knowledge, and we are evaluating by zero shot, few shot, and full shot in performance. So I'm also trying to compare our benchmark with existing well-known benchmark in the ComputerVision community. For example, when we compare with internet and the lyrics of Coco, and for internet and lyrics, so the concept they are relevantly concentrated in a compact domain. And for our method, for our benchmark, and if we visualize the concept, and you can see that it is widely separated in the semantic space, meaning that it could be a better proxy to indicate the cases that we often have for ComputerVision in the world. So in terms of it, and we provide two things. The first one is automatic fine tuning, including learn, read, and APK, so that we avoid the humans or students in the loop to avoid better fine tuning, so that we can compare we can focus to compare different prediction models instead of different fine tuning tricks. So the second thing is that we also provide a toolkit, and which allows to adapt those language image models better. And especially, I want to mention that we propose this language initialization method to initialize the linear head of a classifier. And in the original CLITE paper, they show that they initialize the linear head using a random ways. And in the following experiment, I want to show you that this language aware or this language initialized method is much better than the random initialized method. For example, we are doing it like using different number of training images from like zero shot, few shot to two shot. And we are comparing both fine-tuning setting and linear prodding setting. And in both settings, we see that with language initialization and the proposed, we can adapt CLIP model much better than the random initialization method presented in the original CLIP paper. And one thing I want to mention is that in the original CLIP paper, and we show that few-shot learning result is worse than zero-shot learning result when we only have a few label data. And In contrast to that, we want to show that few shot is always better than their shot if you do the initialization correctly. And the key is that in the pre-training stage, we have pre-trained two models. One is language encoder, the other one is text encoder. The other one image encoder. And it's very important to leverage these two encoders and trying to make the pre-training and model adaptation objective consistent. And while in the original CLIP paper, and we do not use the pre-trained language model at all, and which makes it suboptimal in the model adaptation stage. So we also compare. So even though this benchmark is designed for like the language image models, but nothing stops us to compare it and use it as a common benchmark for all of the image backbone method, including like supervised training method and self-supervised learning method. And in our benchmark, we have evaluated like many well-known pre-training methods for object detection and for image classification. And we are going to show the comparison results in the next slide. So, we compared different settings with different number of training images from 5 shot to the full shot. We also compared in the problem setting and the fine-tuning setting. And our conclusion is that it seems self-supervised learning is like worse than supervised learning, and both of them are worse than CLIP. And note that we are doing the experiment using the automatic hyperparameter tuning, and we do not use the strong data computation, and we do not use some model-specific fine-tuning strategy, as was also shown in their original paper. But we believe our comparison is also fair in the sense that we are doing it in a more automatic way, and we are using simple data computation or standard data computation. And this is the conclusion we get. But it is possible that if we heavily train fine-tune some of those like self-supervised learning models or the supervised learning models, we will get better performance. But this is the conclusion we get. So we also have like two tracks to compare visual pre-trained visual models. And one is the industry track. In this track, we don't have any limit on the pre-trained data, and this is mainly designed for like institute with better GPUs, maybe better data or larger data, and it is designed to test the scaling success of different models, right? And so I think the players in this track will be like the big tech companies eventually. And so we also designed some academic tracks, and which is dedicated to encourage research innovations. So in this track, we limit our pre-trained data to the large public data set, so that we can compare the effectiveness of different training methods instead of which company have a better GPU or larger data. Okay, and the one conclusion is that in our current experiment, we say that language augmented vision model has complete is showing better performance than supervised learning. And we also identify 3 playgrounds to help people to illustrate how they can use this benchmark. The first playground is the sample efficiency. So we encourage people to report the results all the way from their shot, field shot to full shot. And there are, as I mentioned before, and many visual models, large visual models over there in the community. And I think most of them now we are working together to report the results on this benchmark, and eventually we will see like which one is the best one, maybe in 1 month. And so the second playground is parameter efficiency. And so I think overall in this deep learning community, we may have like some common sense. Typically, models with a large number of trainable parameters often lead to better performance, especially when we have enough data, right? And now they are doing like the parameterization model adaptation. It's not surprising that we are actually doing the trade-off, right, between the number of parameters and the number and the final performance. And this is true in our experiment. We say that in most cases, a larger number of trainable parameters lead to a better performance. But I want to highlight that in the data limit setting, it's not the case that a larger number of trainable parameters that often lead to a better performance. And I think, and I encourage people who are studying the model parameterization method to work more to work on this more meaningful section. And in this data limit section, we do have like the problem of the best number of trainable parameters. And the last one is that I want to show that in this benchmark we also have some external knowledge, and I think people can in the future people can try to leverage this external knowledge when we develop this language image model, and this typically leads to like a better transfer performance for either some like knowledge augmented pre-trained model or some knowledge-free pre-trained model such as GLIP. And so the benchmark now is online, and you may check out the datasets and the toolkit and the visit, and let me know if you have some questions. Please submit an issue over there. And we are also organizing the ECCV workshop and challenge, and especially the two challenge based on the benchmark. One is image classification in the wild, where we have 20 image classification data sets. And the other one is object detection in the wild, where we have 35 object detection, small object detection tasks over there. And the goal is to evaluate which one is which foundation model is the best foundation model currently, in the sense that we can transfer to many downstream tasks over there. And so I like to emphasize that this should be a community effort. And in our benchmark, we only provide a baseline comparison based on a small or standard models. And but what is the performance comparison after people scale up the models? And this cannot be done without the support of the entire community, and especially for some models, and they are not public with, for example, the Google Align model, right, and some other models. And but I want to say that we are quite open to try other ways to encourage people to work together to evaluate their model. And it seems that our research community is amazing. And so far, most of the teams we have reached out, they are supportive and to give a try to report their results. And this page shows that some models and organizations that are involved in helping report the results to the challenge. And I am personally very grateful to all of them. And if you are interested in test your method or your model, please download the dataset and give it a try, or let me know if you have any problem. Okay, I think this is all for today's talk. And overall, like I talked about two parts. One is modeling, and the other one is the benchmark. And I think this is a very interesting research direction, and there are a lot of things we can do with OpenSet and transfer level transfer, and this is an exciting new area, and I'm very happy to discuss with you offline for further research ideas. Thank you.
Okay, so hello. So thanks for Chunyuan for giving such a wonderful talk on the topic of large scale models, which I also believe would have a huge impact on the community in the long run. So now let's turn to the audience for some questions. It's the Q&A session. So there are two ways you can ask questions. The first, you can raise hands by clicking the raise hand button in your bottom right on your screen by clicking the raise hands button. Or alternatively, you can ask questions in the chat room if you are not very convenient to speak out. So let's so any questions from the audience, please go ahead. Yeah, so we have Jahao is raising hands. Yes, just to repeat, because you guys, you're all muted, and so in order to speak, you need to raise your hands so we can see you raising hands in the audience, so we can unmute you. Yeah.
Hi, Chunyuan. This is Jahao speaking. Thanks for your wonderful talk. So I have a couple of questions. First is about self-supervised learning. As you have introduced, currently there are two popular paradigms for self-supervised learning, like the transferable learning and the mask image modeling, right? So actually, mask image modeling, like MAE, has shown superior performance than contrastive learning in many downstream tasks. So do you think mask image modeling will take place of the previous contrast learning method, and what different knowledge do they learn? Thank you.
Yeah, well, yeah. Thank you for the good question. So now I guess your question is trying to compare two types of image self-supervised learning method, image contrastive learning method, and the using the, for example, MAE method, right? So I think given my current evaluation, so for example, MAE and MoCo V3, and they are from the same authors, and both of them use the same platform, right? And so I want to, so in this table, you can see that it seems that for image classification tasks, MoCo is giving a better performance than MAE in my experiment, right? And I think overall, like in this community, people have the like some observation that MAE typically gives better performance in a fine-tuning setting, while very bad performance on the linear probing setting, right? And so I don't have a good answer, like what is the advantage of MAE versus MoCo. And but if you ask me, like what is your opinion between image self-supervised learning and language image learning? I think my answer is clear. I would work on language image learning instead of image self-supervised learning in terms of the empirical performance I have ever seen.
Okay, so the next question probably from Yuhang, right? So I think you have been unmuted.
Hi, I'm Yuhang. So my research topic is about open vocabulary object detection. So I have one question about your paper, if the grounded image modeling. So my question is, I see another your paper from Microsoft region-based language image pre-training. So I wanted to know what's the difference of these two papers, the GLIP and the region CLIP.
Oh, wow, that is a wonderful question. So, well, I'm also have both papers, and both of them are both papers from our team. So, so I think there are many ways to distinguish these two, and I think one aspect is region CLIP is based on CLIP, right? And we are still leveraging the CLIP checkpoint. And for the GLIP paper, we do not rely on the CLIP checkpoint, and you can use any pre-trained image encoder and any pre-trained language encoder and build your whole fusion layer and apply the GLIP loss, and then and then you can really have and train it on a large amount of fine-grained image test data, and you have a GLIP model. And this is one aspect. And the other aspect, I think, is related to the two-stage method and the one-stage method. And each of them fall into the one category. And the last part, I think, is if people care more about the empirical performance, which one performs better than the other. And I would say that I don't have an answer if you really scale up both of them. And currently we say that GLIP paper, GLIP shows better performance than reading CLIP. And so because last summer we have limited people capacity, and we decided to scale up one model, GLIP, and on like millions of fine-grained image testers. And we also have a very large model on GLIP, and we show good performance. And in the open set object detection tasks, and we also show it in the task level transfer settings. And I think we have done a lot for GLIP. But if you look back at the region CLIP, and now we are thinking maybe a good time for us to scale up the region CLIP as well. And for this, I think that we are actually thinking about it and work on that.
Okay, so if, for example, if I want to try object level pre-trained models, so you think maybe GLIP is not a good choice, but for region CLIP, you think it also have some potentials to improve.
So if you want to directly leverage one of the so-called best open set OD models, and I suggest you use GLIP because it is trained on a larger data, and we have a much larger model, and you can directly download and adapt it to your new domain. For region CLIP, it has a capacity to do open set OD, but the current checkpoint is limited.
Okay, thank you.
Okay, so so next questions from Wei, right? So I have unmuted you, so Wei, you can directly speak up.
Hi, Chunyuan. Thank you for your great talk. I'm quite impressed by the performance of the models you have achieved in many benchmarks. However, I'm wondering, is there any way to integrate the reputations your models have learned in these models, other than just reporting the performance? Thank you.
Sorry, I didn't quite catch your last sentence.
Okay, and
Can you repeat the question? Yeah.
The knowledge or reputations your model have in, other than just reporting the numbers of the performances.
Which model are you specifically talking about?
GLIP or KLITE. Thank you.
Oh, KLITE. Right. So, are you talking about the inside of the KLITE paper rather than better performance? Yeah, I personally, I really like the insights of the KLITE paper rather than the better performance. I guess the key here is to leverage the free supervision signal on internet. And this means knowledge base, right? So in knowledge base, such as like a dictionary or WordNet or even concept net. And we not only have the concept we have, what we used in training the visual models, we also have their structures. For example, the relationship between the concepts, right? And the definition of these concepts. And so, and those are like people call it a common sense knowledge, right? And I think it is also a type of human supervision of human knowledge. We just contribute and write it down in the knowledge base, right? So, and if you think about definition, so every time when the humans provide a definition to some concept, we often try to use common words or common concept to explain the concept, right? And it's actually naturally translate the real concept to common concept. It's a different representation of the real concept, this common concept, right? And this is the fact that we are trying to leverage in this project. So, for example, we have some rare concept. For maybe next slide is better. We have some rare concept, which is sashimi, right? And if this is like the first time we are in a Japanese restaurant, and we have no idea what sashimi is, but if you look at the knowledge that we get from the knowledge base, right? And for example, there are three types of knowledge we have used in our project. The first one is word hierarchy, and we don't know what sashimi is, but we know what is a dish, what is a food, right? And this, if our goal is to do like some classification task, and we can leverage this concept to help us to distinguish between concepts, right? And similarly, for like the WordNet definition and dictionary definition, and there are some like common concept that actually explain the real concept and help us do better classification. And so if you ask me why external knowledge can provide a better performance, I think the key here is to encourage in trying to improve the overlap between training and evaluation. By this, I mean, the overlap here is defined as the concept that the model have observed in training and in evaluation. And if we can improve this concept overlap, that we can largely improve zero-shot and few-shot learning performance. Of course, when I talk about this concept overlap, I'm not saying that we directly like put the test concept in the training concept, and these two concepts are linked using the definition or the hierarchy. I think this is the main lesson we have learned in this paper.
All right, thank you.
Yeah, thank you for the question.
Okay, so we have a question from Jiahao. So if you guys are asking question, you don't have to mute yourself during the session, because otherwise it will be your side will be muted again, because due to the rule of the Zoom. So Jiahao, you can go ahead.
Okay, thanks for reminder. Hi, Chunyuan. I have another question. Actually, as you have shown, visual language pre-training models have achieved superior performance than language-free or say the vision-only models, right? So, do you think the vision modality, the single vision modality, cannot learn better representations, and it must make use of other modalities to achieve better repetition learning, and whether the self-supervised like the vision repetition learning will finally be replaced by such a kind of vision language pre-training model finally.
You know, this is a very hot debate right now in the community. I'm afraid I cannot give you a very good answer. And so I think self-supervised learning has some advantage, right? Let me give you examples. So in this paper, like I am doing a benchmarking with downstream image classification tasks. But if you use this backbone for object detection tasks or segmentation tasks, I mean those like dense visual prediction tasks, right? And now if you ask me between self-supervised learning, for example, MAE, and language image model, for example, GLIP, which one give you better performance? I would say my MAE may give you better performance for object detection tasks. And it's because for object detection tasks, and so the task actually rely on the region dependence, right? Because our final goal is to highlight which region is the region of interest, right? And this is more consistent with the pre-training objective of MAE, which is trying to capture the region dependency using the mask auto encoding objective. But on the other hand, if your goal is to do image classification, right? For image classification, I think our goal is to the task itself is image level instead of region level, right? The goal is to assign a label or assign a category name to that entire image, right? And this training objective is naturally like similar or equivalent to image language contrastive learning. And so that's why oftentimes we see a better performance when we apply GLIP to image classification tasks. So I think I cannot say that like language image contrastive learning is going to replace like MoCo or MAE in the near future. Maybe what I can say is people will do like a two-stage pre-training. Like, for example, you can do single modality pre-training at the first stage. Then you can do like language image contrastive learning at the second stage, right? And you may have seen the recent paper from NSRA, EEIT3, right? You already see the great performance people can achieve use the single modality pre-training, right? And if you look at the pre-training data in their paper, and the pre-training, the single modality pre-training data in terms of number of images is quite small, right? But and if you also look at the number of image text pairs, and it's also quite small. But it is very impressive to say that we achieve great performance. So can you imagine what if we use like the billions of images or billions of like image text pairs, and we may get that performance, right? So I think one way we can combine this is use any self-supervised learning at the first stage pre-training, for example, EEIT3, right? And then use any self-contrastive learning at the second stage.
Okay, thank you.
Okay, so do we have more questions from the audience? So if you have any more questions, just raise your hand so we can see you. And by raising your hands, it doesn't mean you raise your hands physically, you raise your hand in Zoom. So yeah, probably Yeah, probably no more questions. So I just want to add a little bit more to Jiahao's question about the difference or the advantage of MAE over MoCo. So I recently came across a paper, I think from UC Berkeley, which is visual prompting via image in painting, which shows that by training a model using the MAE style of architecture, you can actually do in context learning, like during inference, which is what has been very popular in the NLP domain. So probably we probably will see more similar or more follow-ups on this trend using MAE like of training for in context learning or prompting for vision tasks. So yeah, if we have no more questions, we probably can we can end the talk here. So thanks again for everyone for attending this talk, and we will see you next time. So bye bye. We can end the session here, and Chunyuan probably we can stay a little bit more after.